Alright, let's look at three-dimensional Jacobian, and we'll compare it to some of the transformations we already know. Now, in a three-dimensional case, the Jacobian tells, if the Jacobian two dimensions and it's any determinant tells how much area is stretched or shrunk, then in the three-dimensional case, the Jacobian is going to talk about how much the volume is scaled. And so the three-dimensional Jacobian, transforming to u, v, and w, is the determinant of x with respect to u, v, and w. The determinant, the partial of y with respect to u, v, and w. And the partial of z with respect to u, v, and w. That means transforming from some region of a function in x, y, and z with your transformations to some, we'll say not region, but we call it space D, and I guess we'll call it some, alright, we're calling our solid regions, we were calling D. So you have some function in x, y, and z, integrating over x, y, and z. You have some transformations, and we'll make that region some larger region G. And then you have some function h in u, v, and w. And you will have your Jacobian and du, dv, dw. Let's look very specifically at a transformation we've done, which is spherical coordinates. So in spherical coordinates, our transformation was rho, x is rho sine phi cosine theta, y is rho sine phi sine theta, and z was rho cosine phi. So what we want to do is we want to find our Jacobian. So, and work on our change of integration. So we'll look for our partial with respect to x, our partial of x with respect to rho. Okay, so the Jacobian question we're going to look for is rho, phi, and theta. So x with respect to rho is sine phi cosine theta. X with respect to phi is rho cosine phi cosine theta. And x with respect to theta is negative rho sine phi sine theta. Right? Taking each one of these. Let's look at y. With respect to rho is sine phi sine theta. Y with respect to phi is rho cosine phi sine theta. And y with respect to theta is rho sine phi cosine theta. Z with respect to rho is cosine phi. Z with respect to phi is negative rho sine phi. And Z with respect to theta is 0. So the determinant we want from this, right, our Jacobian of rho, phi, and theta, is going to be the determinant of sine phi cosine theta, rho cosine phi cosine theta, negative rho sine phi sine theta, sine phi sine theta, rho cosine phi sine theta, rho sine phi cosine theta, cosine phi, negative rho sine phi, and 0. Let's take our downward elements. This times this is 0. I don't know how I zoomed out, but we'll realign things back to where they were. Ish. Alright, now we're taking our determinant. So we're coming down these diagonals. This times this is 0. Plus this times this times this. And I'm going to gather my coefficients. I'm going to rho times rho is rho squared. Cosine phi, sine phi, cosine phi. So it's going to be cosine squared of phi. Cosine theta, so cosine squared theta. Right, but we also had that sine phi there. So cosine phi, sine phi, cosine phi, that's cosine squared phi sine phi, cosine theta, cosine theta. So that got that downward direction, this element, and this element. Now coming down these elements, I'm going to do my rho's first. Negative rho, and negative rho is positive rho squared. Again, I'm coming down this way. And sine phi, sine phi, sine phi. Well, I'm going to sine phi squared, sine theta, so sine squared theta. And I want to keep a sine phi on the outside, right? Because we had sine phi times sine phi times sine phi, so sine phi squared times sine phi. And so those are all my downward elements. Now I'm going to go up. And I'm going to have all these are negative, so minus rho times rho, so that's plus. Let me give myself, so that's plus rho squared. And cosine phi, sine phi. So that's cosine phi squared, sine theta, sine theta squared, sine phi. Right? Cosine phi, sine phi, cosine phi, sine phi, sine squared. So that's these upward elements. Now I'm going to do these upward elements, so it's minus rho times rho, so that's plus rho squared. Sine phi times sine phi times sine phi is sine phi squared, cosine squared theta, sine phi, right? Sine phi, cosine, and so these elements give me this, and then I have 0 here, so plus 0. So let's gather some elements together. I'm going to look at this term and let's see, which term do I want to blend this with? I'm going to also blend it with this term here. So I'll bring these two terms together. I'm going to have rho squared and cosine phi squared and sine phi. Right? cosine phi. So this plus this, cosine squared theta plus sine squared theta. Right? We have a rho squared, a cosine phi squared, a cosine phi squared, a sine phi, so we can pull those out front. And inside we have a cosine squared plus a sine squared theta. Now I want to look at blending these elements here. So I have a rho squared, a sine phi squared, and a sine phi. Then inside I have a sine squared and a cosine squared. And lo and behold, the Pythagorean theorem says this is 1 and this is 1. So I'm left with rho squared sine phi times cosine squared theta, or phi. Right? Rho squared sine phi, pull that out front, cosine squared. Rho squared sine phi, pull that out front, plus sine squared phi, which that's also 1. And so our Jacobian is rho squared sine phi. And that was our transformation element. In fact, if I want to transform from Cartesian coordinates over some d, dy, dx, dz, sorry, got my order a little bit off, to that region in spherical coordinates, then it's some h of rho phi and theta, rho squared sine phi, d rho, d phi, d theta, which we worked out earlier when we were doing our integration in spherical coordinates. So the Jacobian works for moving our boundaries between coordinate systems.